Hi, my name is Julie Lenzer, and I am the Chief Innovation Officer at the University of Maryland and also the founding director of the Quantum Startup Foundry, or QSF. QSF was launched in April 2021 to provide the physical and virtual resources needed to bring quantum technologies to market. University of Maryland is also home to quantum unicorn company IonQ, which is based on the leading edge research of one of our speakers today, Dr. Chris Monroe. Dr. Monroe is a quantum physicist with interest in developing and building quantum computers. He is director of the Duke Quantum Center and a professor of electrical and computer engineering and physics at Duke University. And he's also a College Park professor at the University of Maryland. Monroe is also co-founder and chief scientist at IonQ, a company that is building quantum computers based on individual atoms and applying this incredible computing power to commercial use cases. He's an architect of the U.S. National Quantum Initiative and also a member of the National Academy of Sciences. It is my pleasure to introduce Dr. Chris Monroe.
Okay, thank you, Julie, and thank you to the organizers of this meeting for having me. It's a pleasure to speak to this audience. I'm not accustomed to speaking to life scientists and biologists, but I know that biologists tend to have a collection of hard problems that conventional computers are not necessarily so good at solving. Well, I am a physicist and a quantum computer scientist, and I want to tell you a little bit about the field of quantum computing and how it may change our culture to be able to attack a new class of hard problems. And of course, I will try to touch in particular on biological use cases for modeling processes that pretty much everybody in the field struggles with. As Julie mentioned, I'm the chief scientist at IonQ, a startup company in College Park, just inside the Beltway, and also on the faculty at University of Maryland and Duke University. So you may have heard the terms quantum computing before and maybe ignored it to some extent or thought about how the philosophy of quantum physics is strange. This sounds like science fiction. Well, quantum mechanics is very well established. It's the most accurately tested theory in all of nature, actually. It's a little esoteric because it's not part of our everyday experience in life. Now, when it's applied to computing, using these very interesting laws of physics, when applied to computing, it has promise to totally revolutionize the way we think about computing. And it's very hard to overstate the potential impact of quantum computers. And this plot here generalized human progress over time following the industrial age and the information era in the last part of the 20th century. The 21st century is poised to become the era where quantum information and quantum computing is going to further society, and no more so than in bioengineering and the biological sciences. So, of course, what gave us the information era was hardware and the ability to realize computing elements out of devices that can be scaled. And so this is an example on the left of the physics, and on the right of, you could argue, the engineering and the scaling and the manufacturing of that physics. This is a beautiful picture. It's the first transistor, actually. And of course, our modern day processors are based on exactly this kind of device, only they're made much, much smaller through the invention of wonderful concepts in very large scale integration, VLSI, that gives rise to a chip like this. So the ability to pack transistors on a conventional computer processor has given us something called Moore's law. I'm sure you've heard of that as well. It, in a sense, represents the exponential growth of conventional computer power over the last many decades. This plot shows a log linear diagram of the number of transistors on a processor over the last few decades, and it's roughly growing in order of magnitude every decade, or factor of 2 every year or two. And so we see actually this is starting to taper off. It's still growing. We're still getting more powerful machines, but not at the rate we did 20, 30 years ago. And part of the reason is that the transistors are getting so small that it's very difficult to get them any smaller because they're going to approach the size of individual molecules. Now, I now want to quote Richard Feynman, who is a colorful physicist who worked in the mid to late 20th century, one of the founding figures in quantum physics, actually. Well, he liked to tinker with things, and I think he was very impressed with the solid state transistor and the ability to miniaturize it. And he has this tantalizing line in one of his lectures back in 1959. And he speculated that if we build circuits out of systems that are down at the level of individual atoms, there will be completely new opportunities for design. And the reason he knew that is that at the level of very simple particles like atoms and electrons and photons, the laws of physics are completely different. And whenever the laws of physics change on you, there are many more opportunities to be derived. So I want to talk very briefly about those laws. If you've heard that deep quantum mechanics is hard, I don't see it as hard. I just see it as not. It's an area where we don't have too many analogies in everyday life, and I'm going to apply it to information, the bit. So instead of the bit, we're going to have something called the quantum bit, the qubit, and even at that very low level of computing, the behavior of a quantum bit is completely different and foreign to what we're used to. So here they are. There are two rules, and exactly two rules of quantum physics, no more. They're not hard to describe. The problem is they're sort of confounding. They're not that hard. Okay, the rule number one, and you may have heard this, that quantum systems are waves. A particle is a wave. Well, when applied to a single bit of information, if we think of that as a wave, it can be in a superposition. Again, waves can be sort of all over the place. They're not exactly localized. So when we apply it to a bit, we can store something like this. There's a little abstract jargon here. That's okay. Whenever you see a line in a bracket, that means it's a quantum thing. And this quantum thing is in a superposition of what we label 0 and 1. And this 0 and 1 can be anything. It could be the directions of a magnet. In this case, I'm depicting a single atom with a single electron, this blue dot, but the electron is in two places. It's in two orbits, and that's completely allowed by quantum physics. Electrons do that all the time. And the key parameters are these A and B weights. It tells you how much 0 there is and how much 1 there is. That's sort of the new element here. We now have the ability to store both 0 and 1 at the same time with an arbitrary weight. It could be 50-50, it could be 80-20, and so forth. Now, if you've heard that the math in quantum physics is hard, it's actually not. The math is entirely contained in how A and B can be changed through a wave equation. It's just a normal wave equation like sound waves or water waves or electromagnetic waves. There's really nothing new there, and it's not particularly hard. What's strange is that what does it mean to have a superposition of 0 and 1? And this is why we have to invent rule number 2. And rule number 2, when you think about it, it sounds a little goofy, but rule number 2 says superpositions are fine as long as you're not looking. Okay, so that's a little silly. We don't have any examples of that in life where the act of looking at something would change that something. But that's how we interpret and operationally use quantum mechanics. So the interesting thing happens when you do look, because if you're going to build a computer out of these bits, you have to be able to look and measure them at the end. And the interesting thing in quantum superpositions is that when you measure them, they randomly pop into a definite state. Well, it's good they pop into a definite state because that sort of grounds us in reality. But what's a little bit confounding is that it's random. It seems like somebody's flipping a coin or rolling a pair of dice or something to find out what we're going to get. I mean, Einstein has this famous quote, "God does not play dice." So Einstein was he famously rejected this theory as being fundamental. But actually, this is the way things work, even though it's rather confounding. So indeed, when you make a measurement, you get one or the other, and they come with probabilities. And the probabilities are given by these weights. Kind of makes sense. So if you have a 50-50 superposition, it's like flipping an even coin. Half the time you're going to get that, half the time you're going to get that, okay? Now, probabilities here, you have to use them. And to me, this is one defining strange feature of quantum, is that we have to use probabilities. In every other theory of nature, we use probabilities to express our ignorance. like the weather. We don't know, we can't model everything that's going on in the atmosphere, so we use probabilities. Or even flipping a coin. We don't know exactly how hard we flipped it, so we use probabilities. No, in quantum, we have to use probabilities. And when you think about it, that's kind of strange. Where do they come from? Who decides? It's a good question. We're not going to answer that. It's correct, and this is how we interpret quantum physics. Now let's build a computer out of this. Let's add qubits together, and you can sort of guess things are going to get interesting because we're going to get lots of possibilities as we put qubits together. I think of it as a good news, good news story. So let's follow and make it a little dramatic. The good news is when you put qubits together, you get an exponential growth in their capacity to store states, their capacity to store numbers. With 3 qubits, there are 8 possibilities because 2 to the power 3 is 8. Every time you add a qubit, you double the possibilities. That's because if you have n bits, there are 2 to the power n possible values of those bits, and they all have weights. And so the quantum computer will control these weights and allow them through the wave equation, will control these weights in order to do something. And you might think of doing a parallel processor here where you have a quantum system where you're computing some function of all these inputs at the same time with a single device. So it's like parallel processing, but with one device. That's the good news. You get all these answers at the end. The bad news is that you have to look at it. And when you look at the output of a randomized set of values, you're just going to get something random that doesn't give you any information because you don't know which one you measured. You don't know what input gave the output you measured. So it seems like we're back where we started. But again, with 3 qubits, there's only 8 possible states. If I have 300 qubits, like 300 atoms or something, there are more possibilities than there are atoms in the entire universe. So you can see, even with modest sized quantum computers, we can start to think about problems that would always be impossible using conventional machines. So there is a final piece of good news, and this took until 1990, 40 years after Feynman's lecture, to be realized. And it's a little hard to depict in a drawing, but what I'm trying to draw here is a control sequence that takes all of these superpositions and pushes them, it sort of forces them to a single answer without looking. Okay, we want to preserve these superpositions. These orange dots are called quantum gates. They're sort of like the Boolean logic operations we use in transistors in regular computers, but they're quantum versions of that. They allow us to play with the weightings, and depending on the pattern of these gates, we can get an answer that's very low weight. What I mean by that is that we can get massive interference between all these waves and have maybe one answer or a few answers in the end. And then when we measure that, there's not so much randomness. If the interference conspires to give you this answer, which is the number 5, I guess, that answer can depend on all the inputs. Okay, so this is a very high level picture of how a quantum computer works. And now I want to quickly talk a little bit about applications and where quantum computers look to have some great interest in being used. And then I want to talk briefly on how you build one and where we are, and talk a little bit about IonQ and our approach in building quantum computers. Probably the most famous application of quantum computers is code breaking. Code breaking through the process of factoring numbers. You may not know that most data encryption is secure because we can't factor a really big number. Not 39, that's easy. Well, we memorize things like this, but a big number, this one is not even big enough. We can actually use a regular computer to factor that number pretty fast. But if I give you a number with, 1,000 digits, it'll take the age of the universe and then some to factor it. And this is why we can do encryption. And the way this works from a very high level is if we want to factorize the number 39 in a quantum computer, we create a quantum computer with enough bits to store all 39 numbers. And then we apply gates in such a way that in the end, we get either 3 or 13. And then when we measure it, we're not sure which one we're going to get, but it doesn't matter. If we get one, we can know what the other one is, okay? So that's how a factoring algorithm works. And what's important is that this algorithm on a quantum computer is much faster than what you could ever do on a regular computer. The problem, of course, is that to factor a really big number means you have to store that big number, and you have to do lots of operations. We're not close to having a quantum computer big enough to factor an interesting number, not yet. But I hinted earlier, we don't need thousands or millions of qubits to do something interesting. With only 300 qubits, in a sense, we're gaining access to a configuration space that is super huge. We could never store such a space on a regular computer. So we turn to a different type of a problem, not just factoring, but quantum computers look to be able to solve difficult models. Now, models are all over the place. It's not exactly big data in AI, but how you use that big data to refine models and solve those models, like optimizing a stock market portfolio, or optimizing how certain compounds would interact to create an interesting drug. So there are many types of problems like that in society. One of them is broadly considered optimization. This picture here is sort of obvious. Where's the tallest peak? Well, it's right here. I can see it. It's an easy problem because this landscape has only 2 dimensions, latitude and longitude. But if I give you a landscape, a complex landscape with 10,000 variables, we can't draw it, and we certainly can't find out what the optimum is. We have to test every value. That turns out to be very hard and time consuming, and quantum computers might be able to help in that problem. Another version is a very famous, well-known math problem, the traveling salesman problem. Let's say you want to visit all 48 capitals of the lower 48 states, hitting every city exactly once and minimizing the path. Well, that turns out to be hard. There are many configurations, too many to consider on a regular computer. So a quantum computer may be able to get a better approximation to this type of logistics problem. You can see the value of solving a problem like this to somebody like FedEx or Amazon. Now, turning more on the physics and chemistry side, it turns out that electrons on complex molecules or even simple molecules, they do their own optimization. The electrons somehow magically figure out where they need to be. They just lower their energy, and that's the stable molecule. Like this molecule down here is caffeine. It has about 100 electrons, and if you put these atoms together, the electrons arrange themselves in just the right way. We actually can't easily model that using regular computers. It turns out regular computers, the language of regular bits doesn't capture very well the interaction between electrons, which is quantum mechanical, actually. So it turns out using a quantum computer, we know there will be shortcuts to modeling how electrons arrange themselves, and therefore we can maybe simulate the binding energy of a big molecule. Like this one on the right here, this is a nitrogenase compound. It has iron and molybdenum in there. You might recognize it. It actually fixes nitrogen. It creates ammonia from nitrogen gas, and it's part of what we know allows fertilizer to be made with bacteria at room temperature and standard pressure. It's a very energy efficient process. We still don't really know the details of that, though. So when we make fertilizer, we actually have this very high temperature and pressure process that consumes up to 2 or 3% of the world's energy. It's remarkable. So understanding molecular dynamics, even in this relatively small molecule, could have huge applications in society. Now, turning to even more complex molecules, we see in biomedical engineering there are many potential applications for quantum, all on the computational side. Now, going to more complicated proteins and other type molecules, for instance, understanding the interaction between antibodies and antigens will obviously, in this day and age, we're all thinking about this on how this could help immunology and the idea of engineering better solutions to disease. Now, on a related note, we know that photosynthesis of natural cells is very efficient, almost 100% efficient conversion of light to energy through sugars. And we know that the materials we build are not nearly 100% efficient. And so by reverse engineering photosynthesis with a quantum computer, we might be able to understand how to make better materials for that. There are many problems in biology that involve big data. For instance, understanding the whole genome and how you piece together various sequences of the genome. That's a large optimization problem. There are graph problems associated with that quantum computers might be able to attack. One thing that we're actually looking at the University of Maryland is the simulation of NMR spectra, but with lots of compounds that will allow us to perhaps reverse engineer a complex NMR spectrum of metabolites to maybe in the long run help us diagnosing things. If some marker grows abnormally high, it'll tell you a lot. It's very hard to deconvolve. I'm not an expert in this field, but I mean, it makes sense that it's very hard to deconvolve exactly what's going on when you have interacting NMR spectra like this. So I think the beautiful thing about this field, I think, is that there's so many different avenues of applications. And well, I'm definitely not a biologist, but I'm trying to learn fast. And all of us in the field building quantum computers, we need to know what they're going to be used for, because that'll help us build them for a certain path. We're at the very early stages of these devices, and I'll now for a few minutes give you an idea of that. So quantum computing is somewhat exotic. You might say it's very exotic. It really pulls the carpet from underneath the way we normally think about computing. So the hardware that works best for quantum computers, well, remember that second rule. A quantum system is only quantum when nobody's looking, when it's really well isolated from the environment. And so we look for physical systems where we can get that isolation. They fall into two camps. I would call them natural qubits, natural quantum bits, and synthetic quantum bits. Now, the synthetic quantum bits are built out of silicon or solid state systems. They're sort of built by man, built by hand. And what's exotic about that type of a qubit is they have to be held very cold. They have to be nearly absolute zero. And when you make a computer bigger and bigger, holding it to absolute zero is a real problem. Not to mention that when you make it bigger and bigger, each qubit's a little bit different, and you have to keep track of that. And that's very much unlike what we have in regular computing. Natural qubits, on the other hand, a lot of the hard work is done for us. If I give you a single atom of a particular element and isotope, and I make a bunch of them, they're all absolutely identical. There are no manufacturing errors or defects. Now, we use at IonQ individual atomic ions as our qubits. So these are natural qubits, and they are arguably the leading technology right now in building quantum computers. So I want to show you a little bit about this. The genesis of trapped ion quantum computing started at NIST in Boulder. I was working with David Wineland back then, but since then, Jung-Sang Kim at Duke and I at the University of Maryland have really combined forces to understand how to build a real machine out of these individual atoms. Well, what's inside the box? What's inside the box is actually a hunk of silicon, this bow tie thing, and atoms that float above the surface of that silicon. And this is held in a vacuum chamber, so things are very well isolated from solids and surfaces. They're just held in free space. There's no air to bump into them. And what you see here are exactly 80 atoms. The blue dots, each one's a single atom. It's an atomic ion. They repel each other. And they're not wired together, but we send laser beams onto them to affect operations and gates. And the reason you can see these atoms is that we're shining light right in this picture. We're shining light on them and they're scattering light. And if you're not used to seeing a single atom, it's not very exotic if there's nothing else there. There's no background. And these atoms scatter light very efficiently. So what's exotic here? Well, it's a small vacuum chamber, individual atoms, but they're perfectly replicable and scalable in a way that we can build much larger quantum computers. Down the road from the University of Maryland is IonQ, the company that Jung-Sang Kim and I started several years ago. We're now up to about 90 employees. We're due to become a public company actually very soon. And this is one of our trap chips where the atoms sit just above the surface here. And again, at IonQ, we're leading the way to building quantum computers. And of course, we need to use them for something. We can't just build them with our heads down. So we're trying to form many collaborations, interactions with users or people that have hard problems, which is pretty much everybody. Now, I won't get into details on how our atomic quantum computer works, but laser beams are the eyes and ears on these atoms, and they allow us to wire them together. I say wire in quotes. It's not a real wire, but when we push one atom along, they all move. They all know when we do that, and that's how we make these connections. Okay. Now, remarkably, this system can run at room temperature. We don't need to be cold because of the vacuum chamber, and this is really important if you want to scale up. And again, there's all kinds of software and engineering involved in this that I don't have time to talk about. But because there are no wires, we get to define and turn off wires in software. So it's a very powerful architecture. We've built several generations of systems. We've built 5 systems and 3 more are on the way. And some of our systems are available on the cloud, the commoditized cloud. If you have a AWS account, you can use our quantum computers. Also at Microsoft Azure and very recently Google Cloud Platform. And as I sort of hinted, our technology at IonQ, I mean, this is a scary picture here this is actually one of my labs at the University of Maryland. It doesn't look like a computer, it doesn't look like it scales. But in fact, all of these, this is a physics experiment. And when we understand what we want to do, we can shrink down dramatically. And we have a very well-defined path to scale, also involving vacuum chambers that are pretty small right on the chip itself. And then eventually integrating all of our optical elements on the chip and hooking them up as you would a data center. And all of the fundamentals on all of this evolution of technology, it has been demonstrated, mostly at the University of Maryland and Duke and a few other places. And IonQ is translating that into real products. So to close up, I want to just instill upon you that this notion of quantum computing is quite revolutionary. People don't think in terms of quantum information, the idea of having superpositions. So who should be building these things? I would argue that, of course, universities are comfortable with the rules. We tend to thrive in teaching quantum and things like that, and philosophy and so forth, but we don't build things at universities. And one example I often give is I wouldn't jump in a helicopter that graduate students build, right? I want something that's been well engineered and tested, and they understand the details of the design. Well, industry certainly does that, but industry is not yet so familiar with quantum and the new types of devices needed. And on the user side, I put biotech industry. I think people that do immunology or do metagenomics, they're not so familiar with the rules of quantum. Why should they be? They're not physicists. But with quantum computing, I think I think the culture needs to change because computing is changing. And I think in the interim, we have a big entry for national laboratories to take a lead because they sort of have everything. They have engineers, seasoned engineers that build devices, and they also have the academic mindset we see at universities, and they're starting to get up to speed. And so this is looking very interesting. And it was mentioned that I was involved in launching the National Quantum Initiative, and I think it was an easy call to make because this is really absolutely required for our country to be competitive in the 21st century. And it's not only for data security for encryption I talked about earlier, it's also economic security. I think almost all sectors of the economy will be touched by this technology. So thank you very much for your attention, and enjoy hearing the rest of the talks today.